For the past 2 years, software engineering with AI has been a reactive, handheld process. You write a prompt, you wait for a response, and then you hold the tool's hand through the next step. This manual cycle requires the engineer to curate context, write specific instructions, and evaluate every line of output before deciding what happens next. This approach is structurally flawed. It's a single-threaded sequence bottlenecked by human input speed. Constantly re-explaining context throttles velocity. The right-hand schematic shows the alternative, a recursive, asynchronous system, removing the need for human input stops between every turn. When we treat an LLM as a chat interface, we impose a physical limit on our own scale. In this model, the human is the bottleneck. A shift is occurring in high-leverage engineering. We are moving from prompt engineering to loop engineering. We define a loop as a recursive, goal-oriented system. You provide a purpose, and the AI iterates autonomously on the task until it hits a defined stop condition. The objective is to replace the human as the entity prompting the agent. The engineer moves from being the prompter to being the system designer. Achieving this requires a specific 6-primitive architecture. Without these 6 components, the agent will lose context or create chaos within the codebase. By moving the human out of the immediate execution cycle, engineering effort can shift from manual instruction toward the design of the system that manages the AI. To build this system, the first requirement is a mechanism to surface work proactively. We call this first primitive automations. By using cron jobs and CI hooks, the system handles discovery and triage on a schedule, rather than waiting for an engineer to find a bug or a feature request. This creates the same headache as 2 human developers committing to the same lines without talking to each other first. Primitive 2, the work tree, solves this. It isolates each agent into a separate working directory, allowing parallel execution on the same repository without any mechanical interference. Collisions are eliminated. Branches are self-contained. Cleanup happens automatically. Automations provide the system's pulse, while work trees provide the structural isolation required to scale that pulse without corrupting your repository. With the execution timing and isolation established, we have to look at the environmental context the agent sees. Agents often suffer from intent debt. They start every session with goldfish memory, filling gaps in their knowledge with confident, incorrect guesses. You eliminate this by using skills. These allow you to codify project conventions and historical architectural decisions into Markdown files. The agent reads these every run, ensuring its guesses are replaced by your established rules. But an agent that can only see local files is trapped. It cannot participate in the broader development workflow. Primitive 4, the connector, gives the loop reach. Built on the Model Context Protocol, these allow the agent to read your issue trackers, query your databases, and update your team on Slack. A loop without connectors can only tell you about a fix. A loop with connectors reads the ticket, writes the code, and moves the status to resolved on your board. Skills ensure the loop understands your codebase, while connectors give it the agency to act within your entire engineering ecosystem. The final stage of the sequence involves verifying the work and closing the operational cycle. There is an inherent flaw in verification. A model is often too lenient when grading its own work. This requires the 5th primitive, subagents. You must split the maker from the checker, using separate instructions to ensure the agent reviewing the code is not the one who wrote it. By using a stronger reasoning model for the checker, you create a reliable stopping condition for the loop. However, these multiple verification turns quickly exceed an LLM's context window. Primitive 6, state, provides a persistent record. By writing progress to an external file or a tracking ticket, the system maintains its place between agent runs. The model forgets, but the disk remembers. Sub-agents enforce the correctness of the code, while external state ensures the system can resume its task, making true autonomy possible. These architectural primitives have evolved from custom bash scripts into native features within enterprise-grade tools. Look at how these map to the Codex application. The primitives are represented directly by the Automations tab, built-in work trees and agent skills. Claude Code uses the same architectural shape. Whether you call them cron tasks or scheduled loops, the underlying mechanics remain the same. Codex's primitives are Claude's scheduled tasks. Codex's connectors are Claude's MCP servers. Recognizing this shared structure is vital for long-term strategy. When the shape of the system is the same, the specific tool you use becomes secondary. High-level engineering focus is shifting away from tool selection and toward the design of platform-agnostic loops based on these universal primitives. To see the value of this system, consider a scenario where a CI failure occurs while the engineering team is offline. A scheduled trigger fires, an API connector reads failure logs, and injects context from the skill.md file. The branch is isolated in a worktree. A maker subagent drafts the fix, and a checker subagent verifies it against tests until the gate passes. The system updates the state file, opens the PR, and notifies the team on Slack. In this sequence, manual execution was reduced to 0. The engineer only prompted the system design once, demonstrating the massive leverage of loop engineering. While mechanical execution is finally solved by the system, entirely new risks now emerge for the human engineer. There is comprehension debt, the growing gap between the volume of code the loop ships and your actual understanding of how that code works. There is also cognitive surrender, the trap of blindly accepting AI output to avoid the work of thinking for yourself. An unattended loop making mistakes creates a downward spiral for your architecture. If you walk away completely, you lose control of the quality. In an environment of automated generation, the engineer's responsibility shifts toward shipping code they have rigorously confirmed works. Automated loops make code generation frictionless. This shifts the engineer's core value away from execution and toward architectural judgment and systemic verification.